Okay, let's unpack this. When we think about the rock stars of military technology, the ones that capture the imagination are always the stealth targets, right?
Oh, absolutely. Everyone loves the B-2 bomber or the F-35.
These sleek machines designed to be, for all intents and purposes, invisible. Their whole mission is to slip past any enemy defense without ever even registering on a screen.
That's the ultimate goal of counterdetection, isn't it? To make yourself irrelevant to the enemy's senses.
But if they're invisible, then our deep dive has to shift focus from the target to the eyes hunting them. Because when most people picture how a warship looks for targets, they still picture that big old rotating radar dish.
From classic spy movies, yeah. The one that spins slowly on the mast and goes whoosh, whoosh, whoosh.
Exactly.
If you are relying on that image of the spinning dish today, you're relying on obsolete physics. You are already dead in a modern conflict.
That's starkly put, huh?
Think about it. That dish has mass. It takes physical power and time, often 4 or more seconds, to complete a full rotation. In a modern conflict where missiles are supersonic, 4 seconds is not just an eternity.
It's a lifetime. A target could travel tens of miles before you even get a fresh update.
Precisely.
So the spinning dish, limited by friction and inertia, is completely dead. And here's the fact that surprised me the most from the source material. The technology that replaced it has absolutely no moving parts at all.
None. It's called a phased array radar system, and it represents a total revolution. The ability to look in different directions instantly without any physical movement is entirely dependent on computation.
So we've shifted from a physical engineering problem
To a pure mathematics and software problem.
That is exactly the journey we're taking you on today. Our mission is to understand how a completely stationary device can instantly sweep the sky, and then, crucially, how math can take an echo so faint a whisper and pull it out from all the surrounding chaos. This is the computational battlefield.
And what's fascinating here is understanding the magnitude of the talent shift. We stopped needing the best mechanical engineers for radar. Now we need the best mathematicians and coders in the world.
So let's start with that revolutionary concept, steering without moving. How does a flat, stationary panel on the side of a ship manage to direct a powerful radio beam, say, 90 degrees to the left or right?
Well, we can use the simple analogy from the source material to really grasp this. The old mechanical radar is basically a single flashlight.
Okay.
If you want the light beam to hit a wall on the left, you are forced to physically rotate that flashlight. That takes time. The old system was totally limited by Newton's laws of motion.
And in this high-speed context, that makes it useless.
Yeah.
Physical movement is the bottleneck.
Exactly. Now forget the flashlight. Picture the phased array as a massive wall built out of 1,000 tiny separate antenna elements. Think of them as miniature laser pointers, all facing straight ahead.
A huge grid of individual elements, all capable of transmitting on their own.
Right. And if we turn every single one of them on at the exact same microsecond, all their individual waves combine perfectly, they constructively interfere, and you get one giant, powerful beam shooting straight forward.
Okay, that's the baseline. Simple enough.
But now for the trick.
How do we make that combined beam veer off to the left, even though all those tiny transmitters are still pointing straight ahead?
This is the genius of timing. It's a technique called phase shifting. Instead of firing them all at once, the system creates a ripple effect. A meticulously timed delay across the face of the array.
A delay?
It turns on the element on the far right first, then a few nanoseconds later, the one next to it, then the next, and so on, sequencing the transmission all the way across to the left side of the panel.
So you're basically creating a slight wave of emission, starting on the right and moving left.
Exactly. By perfectly timing those delays, that phase shift, the individual waves arriving from each element don't just add up. They interfere in such a way that their peaks and troughs line up only along a new direction. They build a new, single, coherent beam that shoots off at a specific angle.
Say 45 degrees to the left.
For instance. And that's the key insight from the sources here. The idea that you are effectively bending an electromagnetic wave purely with micro-timing. This electronic manipulation is what we call beamforming.
And because it's purely electronic.
It's instantaneous. I can tell the system to calculate the phase shifts, fire a beam 45 degrees left, and then a millisecond later, recalculate and fire a completely different beam 45 degrees to the right. The speed is limited only by the speed of computation, not mechanics.
And this incredible speed leads to a massive tactical advantage. I know this same principle is used in commercial applications too, right? Like 5G and modern Wi-Fi.
It is. The exact same math is used in consumer tech to focus a strong Wi-Fi signal specifically to your phone rather than just broadcasting weaker energy in every direction.
But in a military context, that speed lets the radar multitask like crazy.
How much multitasking are we talking about?
A modern phased array is constantly multiplexing its beams. It can dedicate beams to tracking 100 or more existing targets at the same time, confirming their speed, altitude, trajectory.
While at the same time.
While in between those tracking pulses, it still scans the entire horizon for new threats.
The analogy holds up. It's like playing 100 games of chess at once, all at the speed of light. It never stopped scanning.
That just perfectly contextualizes why the old spinning dish is so obsolete. If you can instantly sweep, track, and reacquire, you dramatically cut the enemy's decision cycle.
And that capability sets the stage for the second great challenge, which is, overcoming the stealth technology itself.
Okay, so we have our super fast steerable beam now. We blast that focused energy out into the sky, targeting a stealth aircraft. But the entire purpose of a stealth aircraft is to be electromagnetically quiet.
Right, to absorb or deflect that energy so that only an incredibly tiny reflection, an echo, comes back to the radar receiver.
The problem is monumental, though. The reflection coming back from a highly specialized stealth fighter isn't just small. It can be magnitudes fainter than the background noise.
Oh, yeah. Think of the static from cosmic radiation, natural atmospheric interference, even enemy jamming signals. If you were just listening for a simple ping, you would absolutely miss it.
So, how do you find that ghost? It genuinely sounds like trying to hear a single person whisper their name in the middle of a packed, screaming football stadium. The signal is just buried in noise.
That is precisely the detection challenge, and the solution is a powerful computational technique called matched filtering. It completely moves detection away from being a problem of simple amplitude, how loud the echo is, and turns it into a mathematical problem of pattern recognition.
Let's stick with the football stadium analogy because it's so relatable. If I show a simple, hey,
Yeah.
into that chaos, I'm not going to find my friend. How does matched filtering help?
Well, to find your friend, you don't shout a simple sound. You shout a very specific, unique, and relatively long phrase that only you and your friend know. The source materials example is great. You shout, "Cadabra keeps the gate." It's a coded pattern.
And my friend's brain, or the radar receiver, is filtering out all the ambient noise, listening only for that exact unique sequence of sounds.
Exactly. The human brain filters the chaos, specifically looking for that unique acoustic pattern, and when it locks onto it, even faintly, it registers immediately. The radar does the identical thing with radio waves. It doesn't send out a simple short pulse.
It sends out something complex.
It transmits a long, highly complex, unique coded signal. This signal is often called a chirp because it frequently changes frequency or phase over the duration of the pulse.
So the radar is sending out its own custom unique language. This is the crucial step because it guarantees that anything coming back that matches that pattern must be a reflection of its own transmission.
That's right. This is where the mathematical gain comes in. Because the radar knows precisely the unique, complex signal it sent out, it uses a corresponding mathematical template of that exact coded signal on the receiving end.
The template is the phrase, "Cadabra keeps the gate." And the system uses this template to sift through the huge mess of noise and faint echoes coming back.
That is the core of matched filtering. The system takes all the incoming noise, the static, the radiation, the faint echoes, and mathematically slides that perfect template over it, correlating the received signal against it. It's looking for a perfect match in time and frequency.
And the more complex the original signal,
the more likely the system is to find its unique pattern, allowing it to mathematically boost that faint echo way above the background noise.
and what happens when the template lines up exactly with that tiny faint echo that bounced off the stealth plane.
When that precise mathematical pattern aligns with the returning signal, even one that's buried in noise, the computation performs what's called a time compression function. All the energy from that long pulse collapses into a single point. The system registers a massive mathematical spike.
And that's the confirmation.
Boom. There's your target.
And this can't take 4 seconds. This has to happen instantly across hundreds of potential targets.
It requires incredibly fast signal processing. We use highly optimized mathematical algorithms and tools, most famously the fast Fourier transform, or FFT, to perform this correlation in real time.
Let's pause on the FFT for a moment because that sounds like heavy math jargon. But it's essential to the speed, isn't it?
It's the speed driver. Imagine the incoming signal as a complex soup. The FFT is an algorithm that breaks that soup down into its fundamental ingredients, all the individual frequencies it contains. It converts the problem from the time domain to the frequency domain.
Which is computationally much easier for the computer to handle.
Way easier. This spectral analysis makes the whole pattern recognition process exponentially faster.
This synthesized view is amazing. It fundamentally redefines what we think of as the invisible war. It isn't just about physical shapes. It's about algorithmic supremacy.
It is. It's about who has the better math, who can create a more complex signal to shout, and who has the computational power to solve the matching problem instantly.
That is the critical synthesis. Modern detection is a digital dominance problem. Success hinges entirely on two requirements. First, creating a highly complex, unique signal for that filtering gain.
And second, having a lightning-fast hardware solution to execute all the complex beamforming and matched filtering equations in real time.
And this finally explains why the hardware required for these systems is so immense. We're not talking about just a simple computer anymore.
Absolutely not. The need to perform thousands of FFTs and phase shift calculations per millisecond demands massive amounts of processing power. This is why these systems rely so heavily on high-end GPUs, graphics processing units, and highly specialized parallel computing architectures.
And why the parallel computing?
Because the mathematics of the FFT and the matching algorithms are so intense, you can't run the equations one after another. You'd fall behind the speed of light. You need thousands of processing cores attacking the problem simultaneously.
So they break the massive calculation into tiny pieces and solve them all at once.
Exactly. It's no longer about turning a big antenna. It's about turning up the clock speed on the silicon and optimizing the code.
The war has moved completely into the realm of computational electromagnetics. It's software hidden inside a hardware chassis. So thinking about the future, if this level of mathematical complexity is required just to find a current generation stealth fighter, what does the next evolution of this digital battlefield even look like?
Well, that raises the enduring question. As signals become more complex, especially as we move into 6G technology and beyond, the computational resources required for both stealth and detection are only going to increase exponentially. The principles we talked about, beamforming, matched filtering, they're foundational. But the mathematical difficulty of creating a signal that can't be spoofed and then solving the detection equations faster than your opponent, that is the enduring battlefield of modern warfare.